I'm Tim Ventura, and we're joined today by Dr. Greg Hodgin, the Executive Director and founder of Peacebuilding Solutions and the ZC Institute. He graduated from Emory University with a bachelor's in chemistry and from Georgia State University with a bachelor's in history, a master's in political science, and a Ph.D. in political science as well. Greg was inspired by a peer-review paper indicating that a specific class of warp drive is feasible with present-day science and technology, and he enlisted the help of physicists and other subject matter experts to launch the ZC Institute with the goal of developing the world's first warp drive. So, Greg, welcome, sir. Let's get right into it with a bird's eye view of things. Your company, the ZC Institute, is working to build a real-life version of the Star Trek warp drive, more or less. Is there kind of an elevator pitch that you could give me for this project?
There is, actually. And thank you so much for having me on. The elevator pitch is relatively simple, actually. It is the fact that until recently, there was actually no way to really do any kind of warp drive work. A lot of the theoretical work had been done for the past 20 years or so. But now we've realized that the energy requirements that are needed for it have dropped precipitously over the past couple of years with a lot of good theoretical modeling that a lot of these guys have done. But a lot of these guys keep thinking that we can build this thing behind me here, without the spore drive, of course. We can build a warp drive actually with just what we have right now. The problem is a lot of them are missing the power source. So we realized that we can actually use microscopic warp bubbles, quantum space-time distortions, to create fusion, to actually create sustainable nuclear fusion with a decent kind of micro fusion reactor that will give us the power they need to create macroscopic warp drives. So we can build the warp drive. Yes, we think we've got a decent chance of it. Can we do it tomorrow or 5 years from now? Probably not. But 15 to 20? Yeah, we can probably do that. Yeah. But in the meantime, we can solve climate change on the way. So I think it's a pretty good trade-off.
Yeah, well, there you go. So let's dig into the physics a little bit here, because most people aren't going to be familiar with this. Back in 1994, Dr. Miguel Alcubierre, and a lot of people have heard that name, published a peer-reviewed paper describing the physics behind warp drive propulsion. It requires something called exotic matter to make it happen, though, and that doesn't currently exist. We're not sure if it will ever exist. So can you walk me through this general idea of how an Alcubierre drive works?
Sure. So actually, here's this paper right here. Let's see if I get, there we go. Here's this paper right here. It's actually one of the first ones I printed out. 1994, the warp drive, hyperfast travel within general relativity. He did publish it in a peer-reviewed journal, and it kind of did create this small explosion. It does require exotic matter, according to his nice little, his spiel. Exotic matter does exist, but it is very difficult for us to actually produce. There's only two ways that we know of that we can actually produce them. One is, and one of them is still kind of theoretical. One of them is through the Casimir effect. It's when you have two two flat pieces of metal together. There's actually some quantum forces in between that you can actually produce negative matter from, or negative energy from. It's very, very small. We're still working on that right now. The other one is actually a black hole. You can actually absorb and create negative energy from a black hole. Hawking radiation is actually partially derived from negative energy. Basically, long story short, there is no such thing as zero in quantum mechanics, which means that because of that, you're getting virtual particles that pop up into existence and out of existence. So the base remains zero. But if you're producing a positive particle, something that has a positive mass or positive energy, that means you're also producing a negative particle or negative energy, right? But if you're near a black hole and you're near an event horizon, there's a chance that the positive one might get sucked away, which means you only have a negative one left. So it is possible to create it. However, obviously, we have no idea how to create that technology or how to actually harvest it in any way. I mean, hell, we just figured out how to basically create antimatter, and we can't do that very well at all either. Also, his paper basically said, yes, it's possible. We're going to need about 10 times the mass energy of the universe. And the idea is relatively simple. When you, quote unquote, turn it on, you are compressing space-time in the front of you, and you are expanding space-time behind you. Now, space-time is a weird thing. We don't really think about space-time because we live in it, and it's kind of like the force. It's all around us, and it binds us and brings us together, which is kind of bizarre, but it is what it is, right? But think about it like a trampoline, right? And when you take, let's say, a bowling ball and put it in the center, the trampoline is going to dimple down, right? That's what relativity tells us about space-time, that space-time is the trampoline and mass deforms space-time. So if you roll a marble by that bowling ball, it's not going to go straight. It's going to kind of bend around. That's where gravitational lensing comes from. That's where our orbits come from, all that good stuff, right? When we talk about that trampoline, if I bunch up the trampoline a little bit, and I put something on it, and I expand it behind it, I can move. And that's what the Alcubierre drive was basically saying. If you create this massive amount of energy in the front, and you contract space time in the front, you expand it out the back, and you'll have faster than light travel. The problem is it was a high energy requirement, insanely high. It's going to require exotic matter. Yes, it's possible, but it's engineering possible, as in like, sure, we could do it if we had infinite energy and a magic wand. Yes, certainly. So in essence, he said, yes, we can do it, but we're going to need to kill a unicorn to do it. So we don't have any unicorns around. So there you go.
Yeah, yeah. Well, and I should point out, let me point out for the audience, just so that we don't get beat up in comments. Neither you nor myself are physicists, right? So, this is, it's like the medical disclaimer in all those commercials. This is our physics disclaimer, but we both work with physicists, right? As I might say, I'm not a physicist, but I play one on TV, and so, the information that both you and myself have done research on comes from working with a lot of different people. In your case, you've had to vet this through scientists, engineers, physicists, and many others as well. So,
Absolutely.
yeah. Now, so I want to go into paper number 2, because this is the interesting one. I think this is really kind of the crux of what your inspiration was. In 2020, I believe, there was a peer-reviewed paper published by Bobrick and Martyr, which re-examined warp drives and stated that a class of subluminal, spherically symmetric warp drive spacetimes can be constructed based on the physical principles known to humanity today. Right. So this is a follow-on to Alcubierre. They're looking at Alcubierre and saying, okay, this general idea is interesting. It's not workable in current form, but here's a different approach that might work. Can you tell me a little bit about what makes their solution engineerable?
Yeah, absolutely, I can. In fact, it's funny that you read out that specific part, because when I've got this specific part here, I wonder if I can actually get a little. Nope, I can't. So unfortunately, I can't, but that's okay. Oh, I can fold it back. There we go. The part that you're talking about is this part right there, which is it's a little too bright. That's okay. Oh, I know I can do. This can go away. There we go. And that's the part I highlighted. What you just said, literally, is what I have highlighted in my copy of that paper. And the thing is that they took Alcubierre's equations and they sat down. They're like, listen, is this the only way to make this thing work? Because Alcubierre derived one specific thing from the general relativity equations. He said, this is a warp drive metric. These guys said there's a whole subset of these things that we can actually use. And they split them up into 4 classes. And I'm not going to go into all 4 classes right now, but one of the classes was the one that I'm looking at, which is a sublight symmetrical or asymmetrical warp field. It doesn't go faster than light. If you're not going faster than light, you're not going to need anywhere near as much energy, which is where it gets really fun. So when they said, we might be able to build a physical piece. It might be mass, it might be energy. We don't know yet. All we're saying is that the math works. That's all we're saying. And when I called them, because once I read this paper, I said, well, God, I got to talk to these guys. So I went ahead and reached out to them. I said, listen, I read your paper. What are you guys doing with this? They said, well, we don't know yet. We don't think there's much to do with it. But we were looking at Alcubierre's work and his concept, and we realized that we might be able to shave some zeros off the amount of energy that was required, which they did. And so I said, okay, well, that's absolutely fantastic. And I started looking into other papers as well, which I think we're going to go into later on. But yeah, their idea is that subliminal, spherically symmetric, there might be a chance to build those with what we have today. They couldn't give us the idea of how to do it. They said it is possible to do it with what we have today. Now, does that mean that we can do it right this second? No. Does it mean, though, that the unicorn that Alcubierre discussed, it went from a unicorn to a small vial of unicorn blood? It's still impossible, but it's far less impossible now than it was 15 or 20 years ago.
Yeah, yeah. Well, and again, with papers like this, it's just waiting for a physicist to take a hard look at it and come up with yet another innovative idea and then provide another approach. For instance, Dr. Eric Davis, this goes back several years. Dr. Eric Davis did some research into the same specific issue. And if I remember correctly, he was saying that if you rotated the warp field, you may be able to reduce the energy requirements considerably, and that's just one of many potential avenues there. And so, like you were saying, it's still impossible, but it's less impossible. And maybe that makes it a great time to start working towards it, because in a few years, maybe ready. Um, well, if it's okay, I want to jump into the next part here. Conceptually, you've written about this in the past. You've stated that a thin shell of matter or energy in a specific shape warps time. That's the warp bubble itself.
Mhm.
So the shell can either be symmetric or asymmetric in shape. My question is, what is the shell made of? And how much energy is it likely to take to warp space with it? And again, this is the outside of our warp bubble, right? So you've got a
Right.
bubble of warp space. What's this bubble made of?
So that's a very good question that we don't fully have an answer to, but we have some theories. The simplest thing that we could do, and the thing that a lot of these guys are writing about, is mass. You put a lot of mass in there, and if you set them, and if you put that mass in a certain way, be it plasma or liquid or solid or whatever, then you'll be able to warp space time. I don't like that answer. The reason is because mass is, well, it's mass, and there's a lot of it, and you've got to do a lot of things with it to actually make it go correctly. And a lot of these calculations that have been done until very recently have been done with just using mass as what's in the is in the warp shell. In fact, what Bobrick and Martier said was you build the ship and then the ship just goes after you're done building, is what they basically said. You put the last piece in and it just goes, right? That's nice. That's not really useful. That's one of the other issues with Alcubierre's drive and a lot of the literature before 2021 is that once you turn the thing on, you can't turn it off. Because if it's built in a certain way, that's all you can do, right? And especially if you're using mass. Gravity is the weakest of the four fundamental forces. The only reason that we care about it is the fact that it basically extends almost to infinity. But it's very, very weak. Like you can break it right now by picking up something. Congratulations, you've beaten the Earth. That's what it is, right? So the easiest solution, one that we know will work because it happens all the time, is that you can put mass into that warp bubble. However, one, the energy that you need for a warp bubble is directly proportional to the radius of that warp bubble. So the smaller you make the bubble, the less energy that you need.
Hmm.
Most of the papers that were written have set as an arbitrary thing R equals 100 meters. The reason for that is they want to raise 100 meters so they can build this. They want to be able to build a ship. And that's going to take a lot of energy. So one of the questions I actually asked a lot of these theorists was, well, can you make it very small? Can you make it on a nanometer scale or a micrometer scale? And they said, well, I mean, I guess, but why? I said, well, so micrometer, you're cutting 9 zeros off
Yeah.
of your energy requirements. They're like, well, yeah. And I said, well, why does it just have to be this? The thing about general relativity and quantum explains three forces. General relativity explains one, and they don't overlap. There's some weird. It just doesn't work. You cannot use one with the other, and there's a lot of talk about that's a problem, right? The standard model shows us that we can explain three forces pretty well, but we know it's not perfect. General relativity is very good, but it doesn't explain quantum. There must be some sort of overlap. And because of that, and also because of our good friend Einstein, guess what? E equals mc squared. We know that energy and mass are actually interchangeable. Once you realize that, you can use different things. So there's actually a discussion of whether we can use certain types of electromagnetic radiation to actually make this happen, radio waves, possibly ultraviolet, infrared, something like that, or electrical charge. Electrical charge is my personal bet. I'm probably wrong, but that's okay, because you can pump electrical charge up pretty high, and you can kind of go from where you want to with respect to that. So the shell itself will be very, very thin because it's got to be very, very dense. So we're talking like millimeter or a micrometer or something like that, no matter what you're doing, right? It's either going to be a great deal of mass or it's going to be a great deal of energy in that shell. And again, if we're discussing symmetric versus asymmetric, a symmetric warp bubble is actually going to have the same amount of energy or the same amount of mass all the way around to create the same distortion. And the asymmetric one will have more in the quote unquote front so it can move forward and less in the back so it won't do anything of that nature. But again, we're not sure, and this is where the speculation comes in. We think we have a pretty decent idea of what will work and what won't, but until we actually do the full proof of concept, we're not going to know yet. So that's where we are right now.
Okay. Okay. Well, and I do have a list of questions that I'm working my way down. But I do want to interject though. What you're saying about nano and small sized warp bubbles, to me, that resonates very much with what's going on in space today, right? The idea, this 20th century paradigm was we're going to build it big, we're going to go as far and as fast as we can possibly go and take as much as we can with us, and probably the height of our hubris was the Orion ship, right? In the mid 20th century, where we're literally just going to have a metal
Let's
plate,
dump
drop a
nukes out the
bomb.
back.
Yeah,
Yeah.
I mean that was that, and that's I mean I would consider that's like that's the big block 350 of the spaceship world, not real efficient, but it's going to take everything with it. So, in contrast, today's space industry is looking at stuff like small sats and CubeSats, and they're even looking at how they can make things smaller, having lots of small satellites because it costs less. And for the payload where you could deploy one large satellite, you might be able to deploy an entire constellation of others. In terms of warp drives, you are looking at something that is very similar. I like that idea. I like the idea of being able to miniaturize it. So.
Well, that's definitely a big part of it. But the thing is that we can't build the big ones until we have the decent power source. And I want to build the R equals 100 meters. I want to make it big because you can't send someone through space on something that's a micrometer. You can't. But we can build something where we can, as we learn how the technology works, we can make bigger and bigger and bigger warp bubbles, which is the goal. But right now, yeah, we have to start small because there's no way we can create anything in the lab that's going to be larger than a micrometer or nanometer or anything else of that nature. Yeah. So yeah, I definitely want to start small, but I want to stay small too for a while because the longer we learn the longer we take to learn the properties of the warp bubble, the better idea we have of how we can use it effectively. It might be useful in other industries or it might not. But until we actually figure out the specific properties of the warp bubble, we're only playing in guesswork.
Well, and so I want to go to basically inertia and movement inside of this. And for me, that's really interesting. Now, in Star Trek, in the TV show, when they accelerate, they don't show visible acceleration, right? Which comes in very handy on a TV set. But in real life, it turns out it may be the same. And the reason I mention that is you're curving the geodesic of space-time. And so a lot of people have wondered, well, what's the acceleration going to be like, And if properly constructed, yes, as you're holding your hand up, that acceleration could be zero. So that may include not only acceleration, deceleration, but also like a change of velocity, change of direction, anything along those lines.
Correct. That's exactly right. And in fact, the idea is that, and you can go FTL or not. And then the nice thing about the system that we're thinking about and we're trying to design, that we're working on designing, is the fact that between FTL and sublight, oh, excuse me, it's 10 o'clock where I am. Besides, FTL and sublight are not this massive barrier. It's almost like the sound barrier, where it was an engineering issue. And I'll get into why that is later on. But what's inside is not inertial. So whatever inertial frame of reference you were in when you started is the one that you'll be in when you turn the thing off. For instance, if you're on the planetary surface and you go 10 miles up with a warp ship and you stop, you're still in the same inertial frame. The problem, of course, with a non-inertial thing or any kind of non-inertial engine is the fact that once you cut it off, you're not going anywhere. So any other external forces will automatically begin exerting its force upon you. So if I go 10 miles up and I turn it off, I just start falling. Which is kind of a nasty thing. So if your warp drive goes down, it's not like Star Trek where you're just kind of waiting around. You're just going to fall to wherever. There is no other way. That's why we're looking at a backup propulsion system. But from an outside observer, yeah, you're going as fast as you want to. From inside, it's like being on Earth. You're sitting in a chair and just everything's moving around you. And it's almost like a space-time elevator. You get in, door closes. You don't have to look out. It doesn't, for a second, it might feel like you're moving. Maybe not even then. Once you get moving, you don't feel it. And then when you stop, you open the door and you're in a different room, right? You're in a different floor. It's the same concept.
Okay. Well, so I want to go to theoretical physicist Eric Lenz, who's found some geometric solutions that reinforce the Bobrick and Martyr work that initially got you started. And you also mentioned that Fell and Heisenberg have done work that reinforced this same paper. With work on positive energy warp drives from hidden geometric structures. So it sounds like you're not just drawing from one paper. It sounds like you've been able to kind of backtrack this and find support for this in several different areas. Okay. So we've got like about 3 inches of supporting material there then. Lots and lots.
And this is actually relatively old. A lot of this starts from 1994 and goes on, but a lot of this stuff is 2015 plus. And now there's a lot more literature coming out from 2020, 2021, 2022. Of course, peer review is not easy, but a lot of people have been responding to Lenz's paper. A lot of people responding to Fell and Heisenberg's. And of course, a lot of people are responding to Bobrick and Martier as well. And so it's not just one paper, which is why we're saying there's a number of theories that this can go by. And they're thoroughly grounded in general relativity. Lenz flat out says in his paper, listen, if you do it my way, with mass alone, you can warp space-time with 0.1 solar masses with a radius of 100 meters. Now, that sounds like a lot. 0.1 solar mass is a lot. It's a lot.
Yeah.
But that's R equals 100 meters. Let's talk about a nanometer. Now I've cut what? Nanometer is what? 10 to the negative ninth. So now I've cut what? 11 orders of magnitude off of it. That's a lot. Now he's still just using mass. If we use energy, if we're using electrical charge, now we've gotten to somewhere where we can actually do something. Now, whether that's the case or not, we're not entirely sure. But that's part of the reason we need to go and do what we need to go in the first place. But the fact that people, in fact, there's one of my guys is actually literally doing an experiment, probably within the next couple months or so, on whether this works with radio frequencies or not. Mm. And his goal is to create a very small microscopic warp bubble inside of a basically warp plasma is his idea. So there are several people who are doing this, and these are not just people who are building stuff out of wood in their basement or anything like that. These are people who are publishing in peer-reviewed journals, because there's a lot of people who said they've done something like this many times before, but they don't get peer-reviewed. They don't have anyone replicate their studies. Part of our business plan is to make sure that anything that gets found in the lab, we replicate somewhere else where those people have nothing to do with it, because let's be honest, we all want this to happen, and we all want it to happen so badly that we're going to have this positive observer effect of like, no, I saw it. I really did. But did you? Are you sure? And before we go and say we did it, we want to make damn sure that we did it. An excellent example is the fusion guys who said they actually did a sustainable fusion for a while, and then no one could replicate the experiment. Well, then you didn't do sustainable fusion. Sorry. If you can't replicate the experiment several times, then that doesn't matter to me. I don't care. It's probably a fluke or something like that. When the Large Hadron Collider said they measured something going faster than light, and they realized that someone had unplugged something, hey, that was cool, but I'm glad you came out and told us that that's not what happened. So yeah.
No, it happens. It happens. So in the engineering side of things, for these symmetric microscopic warp fields, as you guys design these in order to better model and understand how to control them, what kind of power are you going to have to put into this? Would you guesstimate just to get started? I mean, we're talking tiny little warp bubbles here.
We're going to be talking megawatts of power at the least. And it's going to be, that does not mean we need to build our own reactor, but we're going to have to call the substation and let them know we're going to be drawing some juice, right? On the flip side, you cannot use a lead acid battery for this. This is not, you're not going to be able to plug in 6 AA's from Energizer and make this thing happen. It's going to be a decent amount of either electrical charge or radio frequency, or if worst comes to worst, mass. Like, it doesn't matter in that regard. It's not going to be something that you can do. You can't do that in your basement lab unless you've got that thing really set up. You can do it in a well-furnished university lab that's set up for electromagnetic work, electrical work or magnetic work, and or set up for EM work. I think that will get it done. Like, let me put it this way: if you can run a decent NMR, I think you'll probably be able to run. You'll probably be able to at least be in the same ballpark as what we're doing here.
Okay. Well, actually, that's interesting, because another aspect of this, and this is my next question, but if you're working with megawatts, for a moment I thought you were going to say 1.21 gigawatts, and then I realized that's a different movie, right? So
it is a different movie, and honestly, if as the warp bubble gets bigger, we're going to need 1.21 gigawatts. That's fine.
At some point,
we'll discuss Mr. Fusion down the road. I promise you, he's coming back, so that's okay.
Yeah. So the interesting thing, though, is when you're working with megawatts, you guys are looking at a pulsed mode warp drive. And yes. So when you're doing initial testing to create these warp bubbles, it's possible, at least it seems possible to me, that you may be able to create these in a pulsed mode, right, for a split second to do some testing and modeling there, as opposed to having to create a continuous warp bubble. So again, that puts it closer to energy levels that we can work with.
Even better. And this is where my excitement really kind of comes in with respect to this. And when I've talked to some of my guys, are like, you might not be wrong, which from a theoretical physicist is a very high thing. That's a wonderful thing to hear when they say you might not be wrong. I cried. I was so happy. They said, and I quote, I apologize. Oh, goodness. They said, well, when I told them what my idea was, which is, in essence, when we discussed the shell, in fact, can I share my screen with you?
Yeah, go for it.
The idea is that you'll see that there's a very thin purple piece that's kind of surrounding this right here. That very thin purple is going to be a magnetic confinement of some way, the magnetic bottle or something like that. And the reason for that is because that red part Oh, excuse me. I'm sorry. No. The red part is the red part's going to be high energy charged plasma. So, and we're thinking it might be electrons or protons. It might be radio waves. It might be something like that. We're not sure yet. But the red part's the juicy filling of the pie, right? Whether it's electromagnetic force or electrons or magnetism, whatever. The very inside, the black part is the warp bubble itself. Okay. Now with it on, and again, you'll see it's very small, 1 to 2 angstroms. It might be 1 to 2 nanometers, 1 to 2 micrometers. We're not sure yet. This is when it's turned on. What matters is that the density inside, the mass or the energy inside, has reached a certain density, which will actually, and a certain geometry, which will allow for the warp field to actually be created. Okay. So to turn it off, all I have to do is move the magnetic field out just a little bit.
Okay.
Once I do that, I've dropped the density enough where the warp field shuts off. But I have not drained the warp field, have I? Because of that, all I can do is I can reinsert the magnetic field, and it'll look something like this, where it turns on and off because I'm expanding and contracting the field. Now, whether I can do it this fast, I don't know. We're not sure, but that's the idea. So because I'm making it so small, and because we're using these kind of things, I can turn it on and off as I want to. Now, how fast things flow in and out, we're not sure. But the point is that once you reach that critical density, the warp field turns on. Once you go below that critical density, warp field shuts off. Okay. And so it doesn't just help with energy consumption. It does, because I'm putting the energy into the warp bubble, right? But nothing is leaving the warp bubble, which means once I get it charged, I can just keep going. I don't have to keep dumping energy into it, which is good. 2, that means that I can control when I can turn the damn thing off, which is also important, because as we discussed with Alcubierre and the other drives, you build it and you turn it on, it just stays on.
Yeah.
Ours, you control when it turns on. So we can pulse it and do all kinds of things with it. I can turn it on and off several 100,000 times a second. And because the warp field is so dense, there's a chance that this warp field itself, like the what's making the warp field, actually acts as a radiation barrier. So when I turn on, I can't send radio waves. I can't send electromagnetic radiation in and out of it. But if I turn it off, everything can come back in again, right? I can get stuff that comes back in. So we've solved a lot of the telemetry issues, because one of the things with Alcubierre is once you turn it on, you kind of divorce yourself from the universe.
Yeah.
But I'm doing the same thing. But I'm not, because as I turn it off and on so many times, I can still get telemetry data coming into the ship or into whatever I'm doing several 100,000 times a second, or however often we can do it, right? So yeah, the pulsing is insanely important when it comes to what we're talking about. It gives you much better control of the system.
So I guess what I should ask next is, you have a warp bubble in place. It could be steady state, could be pulsed, as you just described. How do you move the ship forward? Or okay. Again, it doesn't have to be a ship. We're talking about very small ones to begin with, but with whatever is inside of the warp bubble, how do you propel that? Maybe that's a better way to ask it.
So there's 2 types of warp bubbles, symmetric and asymmetric, right? Symmetric is the one I just showed you, where the density of charge or density of mass is the same all the way around, which means I'm distorting space-time around it all the same way. Asymmetric is where I'm actually bunching up some of the charge or some of the mass in the front. That will contract space-time in the front and expand it in the back. And that's how you move it, because in essence, you're almost, I hate this. It's not the best analogy, but it'll work. You're riding a wave. And it's just, you're the one who's generating the wave. And so you create it, and you're just kind of moving along because you're getting dragged along that space-time with the warp bubble itself. That's how it's going to work. And the more energy you put in the front, the more you drag along. Now, our idea is that you don't build a big one that drags along meters and meters or kilometers or light years at a time. You build one that just drags along a millimeter at a time or a centimeter at a time. But each time that I pulse the warp drive, I'm moving another centimeter, another centimeter, another centimeter. That way, I don't have to do these massive space warps. I'm just doing it very small. But by turning it on and off, they can build up very rapidly. So if I'm doing a centimeter at a time, but I'm doing it, at a megahertz, well, now I'm going pretty fast. Like insanely fast. And yeah. I'm still using, don't get me wrong, I'm still using a great deal of energy to make it go. Don't get me wrong. But it's nowhere near as much as we thought would be beforehand by building it and leaving it on continuously, because then you've got to put all of it in, and then you're going all kinds of crazy stuff, right? So this saves on energy, and it also, and even better, because you're doing this, and because if it's set up correctly, you can do it this way. While I'm moving forward, if something's in front of me, if there's an object in front of me, I'm going to get telemetry that says there's an asteroid in front of you. Okay, cool. Because it's not inertial, I don't have to stop. I can just, my next few pulses will just be going 90 degrees to the east or 90 degrees to the west. I can skip around it. So I don't have to continuously go forward. The continuous warp drive, if I cut it off, I'm losing all that charge or I'm losing all that mass. So once I cut it off, I got to recharge the whole thing to turn. So once I turn one that's continuous on, it just shoots in that path forever or until you turn it off. Ours, on the other hand, because we are not draining it each time, we're just expanding the field each time and contracting it again. We're not, I mean, of course, we're going to lose some energy because, I mean, let's be honest, that's thermo. That's just the way it is. You can't get perfect. But it'll be much less to just keep it fully. In essence, we're topping off the tank each time.
Yeah.
As opposed to, I need to turn. Well, shit, now I got to turn the whole thing off and then reorient and then get it back up again. Alcubierre's drive reminds me of Star Wars' hyperspace and the hyperdrive. We're like, you jump in and you're just, that's it. And whatever path you're in, you better hope you calculate it right because if you didn't, you're screwed. Ours is much more like, it's actually a bit more like Trek. Like it is a bit more like Trek, not perfectly because Trek, you can still stop and everything like that, but they don't. But you can change your trajectory while you're in warp, and they've seen it several times. You're like, we were going here, now we're going to go here. You never see them drop out of warp. They're just moving. We can do the same thing with ours, we think.
Okay, so there you go. And in terms of topping off the tank, and again, this is my next and actually my final, well, my second to final question, but you can use this, you believe, to generate fusion reactions to power the system as well. So these warp bubbles, if I understand correctly, basically by modifying time space, you can destabilize nuclei of some types to produce fusion reactions. Is that kind of the idea?
That's kind of on it, but it's really, really simple. It's actually insanely simple when you think about it. All we're going to do is, if you got hydrogen nuclei floating around or hydrogen atoms floating around, the thing that causes them not to fuse is the Coulomb force. Positive hates positive, negative hates negative. When they get close to each other, they repel. One of the main reasons why fusion works the way that it does, the way that we're trying to do it terrestrially, is we're trying to heat plasma up to a really high temperature and spin it really fast. You need high temperature and high pressure to overcome these Coulomb forces. And so we're either using a tokamak, where we're spinning things up really fast and smashing them into each other and hoping for the best, or we're using laser confinement, where we're shooting lasers at like a deuterium pellet and hoping for the best. Now, the sun, the reason that the sun works the way that it does is because it's really big and gravity just crunches stuff until it forces it to actually fuse, right? We can't do that here. Well, until about 100 years ago, we couldn't fly either. And we realized there's a nice little quirk in physics. It's called the Bernoulli principle, about airflow, because airflow goes over this one. And if you shape the wing in a certain way, you can literally fly a plane, right? And it's a weird quirk in air pressure. That's all it is. Well, turns out that we can do the same thing with this, because if I have a number of small microscopic warp bubbles set up in a certain geometric way, and I have a volume, and I put a bunch of hydrogen in that volume, then I turn the warp bubbles on, the volume collapses to whatever we want to. I don't need high temperature and pressure if I can create my own. Why do I need high temperature and pressure where I can literally force hydrogen atoms to fold on themselves and to be next to each other? That's how we overcome the Coulomb forces. And when you get them close enough, they begin to fuse. Even better, I can leave it on because it's pulsed. Remember, I can leave it on for 5 seconds. So if that's how long it takes for it to fuse, cool, 5 seconds it is. Then I can turn a couple of them off and have an exhaust valve, basically. So you have intake going in, you get the crunch, and then something pops out, right? And when I talked to my fusion guy about this, and I'm not making this up, I went to go visit him in Huntsville, and he was when I talked to him about what he was doing some cool stuff with dielectrophoresis and some other stuff like that, which is really fun. And when I told him what I'm doing, he's like, he basically like jumped up and clapped really hard, like he was a 13-year-old girl at a K-pop concert, because he understood that he was like, this fixes almost all of our problems with fusion. Like, this is ridiculous how this makes it work. He's like, but we have to make sure. Yeah, and his problem was, he's like, but we have to make sure that the pulse that we creates more energy than what goes in. I said, but it doesn't, because if it's already charged up and we're using multiple pulses, the first pulse will actually give you an energy negative return, right? But each pulse, you can recharge your battery. And then after a certain number of pulses, Well, now you're producing a profit every time. So it's almost like starting a car. It's a big battery. It's not a lead acid battery. It will take probably several rotations and several cycles of this quote unquote engine to work. Once you get that thing charged up, now you can do whatever you want to. Even better. And we had this conversation offline. Back to the Future at the end of the movie when Doc Brown drives in to go get Marty McFly and his girlfriend
Mr.
Jennifer.
Fusion. This is Mr. Fusion. Yeah.
He pops open Mr. Fusion, right? And he goes to the garbage can and just starts dumping random stuff in there. It was not random. You'll notice that it was all organic. That's carbon, nitrogen, and oxygen. And because of that, those are all things that you can fuse for energy. You can fuse energy all the way to iron. Iron is your dead sink. That's it. Fission breaks down to iron. Fusion burns up to iron. Okay. So if I'm even aluminum, so he could have dumped the can in there. So aluminum, beer that he dumped in, or all the other stuff. If depending on how we do it, probably this is going to be something that one of our labs is just going to do full time. Is what are the conditions that each engine needs to burn organic matter, to burn aluminum, to burn whatever, right? Because I don't need just hydrogen anymore. Hydrogen's the easiest. Do not get me wrong. Like I would love, because that's just water. And I'd like to point out here, I did not say deuterium or tritium. I just said hydrogen. We don't need deuterium or tritium. We just need protium, which is just basic hydrogen. And that means that you can really stick your pole into the water. Didn't say fresh water. Pull that stuff out, reverse osmosis. You can pull out your water. You use hydrolysis on that one for a touch of sulfuric gas. You get your hydrogen gas, stick that in, you call it a day. So if we have this designed correctly, these microscopic quantum space-time distortions, we create this artificially small vacuum place where we can put these things that fuse. You start producing the energy. Now that I have the energy, now that I have the megawatts or the 1.21 gigawatts power that I require to run my time machine, great. Now I can begin building bigger and bigger warp bubbles. And that's part of our business plan, is the fact that with each set of patents, we're patenting a larger warp bubble, and we're patenting a larger one. That way you can kind of keep going. And someone said, well, your patents will expire in 20 years. Yeah, but by that point, we have the best warp lab in the world. Like if you want to go ahead and play with first edition, go right ahead. Now we've got ninth edition that has and even better, we're going to be doing a lot of computer simulations as well, because once we get the properties of the warp bubble, stick that in the computer. What's the best geodesic to fly in an atmosphere? What's the best geodesic to fly in space? They might be different. We don't know. What's the best geodesic to fuse protium versus helium versus carbon versus nitrogen? Is it how many warp bubbles do you need to create this? What's the minimum? What's the maximum? All that good stuff, right? And fusion for me especially is kind of a big thing, because that's solving climate change. We can solve the world water crisis. We can bring our civilization to Kardashev 1. And that's not even building the warp ship yet. Like we're not even there yet. Like we can change humanity even without building it yet. I want to build it. I like this. I want this. But getting there, a lot of people said, if you've ever seen South Park, the Underpants Nubs, like step 1, collect underpants, step 2, question mark, step 3, profit. A lot of people who are looking at warp drive were going, oh, step 1, build the warp drive. Step 3, we go FTL. Where's the energy source in step 2? How do you power the damn thing? Because the Discovery and Enterprise D did not run on coal, for God's sake. You need fusion. And this is one, and even better, a lot of people go, I don't want, warp drive will take 15, 20 years. Yes, it will. So putting money into someone who wants to build a warp drive, you're not going to get money back for a long time. That's a Hail Mary. Putting money into something where you can get your money back in 5 to 10 years because we're doing sustainable fusion and we can basically corner the world energy market. Well, that's a bit of a better bet, isn't it? And then once I get that, then we can go and have fun and build the Phoenix, which is the point, right? So yeah, it's so cool when you think about the number of applications you can have for it. But for us especially, it's energy production, energy generation, energy production.
Okay. Well, Greg, on that note, let me thank you so much for your time today. And let me close by asking, what comes next in this project for you?
So we're waiting on an NSF grant right now because we signed an MOU with the University of Alabama, Huntsville. I'm hoping we get it. We might not. I'm crossing my fingers. I'm hoping we're getting it. If we don't, we're going to start for the next grant cycle with the DOE, NASA, and DHS. But we're, of course, right now looking for private funding. I have equity, and I'm happy to hand it out. And we're looking for people who believe in what we're doing, because let's be honest, right now we're at a position that, imagine if you were the person who seeded agriculture, like literally gave someone money for agriculture, or gave someone money because he had this weird metal stuff that he put on things that he was able to like stamp paper with, and he was able to make new stuff with it. And it's crazy. It's crazy. I know. Or maybe this guy has this idea, like maybe if I could build cars in a certain way, like in a factory with an assembly line, you know, you could, whoever we're talking to, that's what I'm telling them about is like, you could be that person. And the fact that this is going to have them, if this works out the way it looks like it will, and I think it will, if I didn't, I wouldn't be doing this. This has the potential to radically change human society more than the industrial or the Neolithic revolution. This could change us more than agriculture did. And that's insane when you think about it. So where we are right now, we're in the same crappy spot that a lot of other people are. We're chasing money, but I think we've got a lot of good leads, and we're looking at a lot of places that will actually give us where we need to go. And then we can solve a world energy crisis, and we can give humanity the stars. And I can't think of anything better to do.
And there you go. Thank you again so much for your time today, sir.
Thank you so much, Tim. I appreciate it.